Okay, good day everyone. Good day everyone. Our topic for today will be about summarizing and organizing data, which means we will be discussing different methods on how to summarize and organize data. Especially, we call them ungrouped data because group data were already summarized and organized. There are three major methods in summarizing and organizing data. So the first one is the tabular method. Then you have the graphical and the numerical method. Our focus for this lesson or for this meeting would be about the tabular methods. Under tabular methods, we also have the different forms of tables. Now, we will only be focusing on these three, though there are a lot of them, but we will be only focusing frequency distribution table, cumulative frequency distribution table, and the stem and leaf table. Let's start with the frequency distribution table. Now, this is your frequency. This is an example of your frequency distribution table. Now, a frequency distribution table, and the other remaining tables have parts. Now, we will identify them one by one. First is we have the table number, then table title, column header, row classifier, body, and the source. Table numbers are named table 1, table 2, and so on. Now, it depends on uh, how many tables you have in your data or in your presentation or when you summarize your data. Then, next is the table title. Sorry for that arrow, that's on the table title. So in the table title, it's like a summary of what will you be seeing in your table. So for here, for this example, you have distribution of students in the junior high school according to year level. Mm, okay. Then you have the column headers. Now these are your headers, or this is your column header. We have two columns here. So you have the year level and the number of students. We also have the row classifier. So commonly, or not commonly, the first column, the rows in the first column are called your row classifiers. So you have here, for this example, you have our row classifiers are the year level. So you have first, second, third, and fourth years. Then you have the body. Now this is the body or uh, the numbers. Okay, if you have multiple columns, for example, 3 to 4 or more columns, so the body would be from the second column until the last column, excluding the header, of course. And the last one is the source note. When you say source note, if this is not your data, or wherever you have taken your data, so you would place it under the source note. Now, it's not if your data is taken by you, or if you have gathered the data, then you don't have to put on the source node since it's yours. Okay? Again, these are the parts of a frequency distribution table. Now, let's go to the calculated parts. So we have these parts: class interval, lower limit, upper limit, class width or class size, then the frequency, the class boundaries. We have the upper class boundary, the lower class boundary, the class marks, the range, and the relative frequency. Okay, suppose we have this example. So we will consider this table and we will identify different calculated parts. Now, for this table, we have 6 class intervals. Now, you can identify the class intervals of the table based on the number of row classifiers. So For here, we have 6 rows, which means we have 6 class intervals. That's 5 to 9, 10 to 14, 15 to 19, 20 to 24, 25 to 29, and 30 to 34. Now, we also have this, no? Under the interval, we have the lower limits and the upper limits. Now, these numbers here are your lower limits. Okay? So 5 is the lower limit of the first class interval. 10 is the lower limit of the second class interval. 15 is the lower limit of the third class interval, and so on. The next one are your upper limits. When we say upper limits, so these are the largest number for each or in each class interval. 9 is the upper limit of the first class interval. 14 is the upper limit of the second class interval. 19 is the upper limit of the third class interval, and so on. Next column. Before that, so how do we calculate the class width? Now, if you have a given frequency distribution table, how do we calculate the class width? So the class width can be calculated based on the upper limit of the next class interval minus the upper limit of the current class interval. For example, if we will refer to the first and the second class interval, our next class interval is the second row here, row classifier, and this is our first class interval. So the upper limit of our second class interval minus the upper limit of the second class interval. We can also calculate the class width using the lower limits. So that's the lower limit of the next class interval minus the lower limit of the current class interval. So if we will use the second and the third row classifiers as our intervals or reference, so our current class interval is 10. So that would be 10, and our next class interval is 15. So that's 15 minus 10. So for this example, our class width is equal to 5. No? For if you will refer to the first and the second class intervals or the row classifiers, which are these 5 to 9, 10 to 14, you have 14 minus 9, and that is 5. Or if we will use the lower limits, so this is L, by the way. Now, if we will use lower limits, uh, we'll use a pen. So we'll change it to L. Okay. If we will refer to the fourth and the third one, so our lower limit for the fourth class interval is 20, and the lower limit of the current class interval is 15. So that's 20 minus 15, that is equal to 5. Next parts are the boundaries. No? We have the lower class boundaries. So for the first row or first class interval, our lower class boundary is 4.5. As you can see, uh, our boundaries have one more decimal places compared to our intervals. So that's the rule. No, you have to have one more decimal place compared to the class interval. Then how do you calculate the class boundaries? So you have just to add the upper limit of this class interval, then add it with the lower limit of the next class interval and divide it by 2. So that's 9 plus 10, which is 19, divided by 2, and you have 9.5. Then you just subtract 9.5 by the class width, then you will get 4.5. Then the next rows will follow. So add 9.5 by 5, which is our class width, so that's 14.5. Add 4.5 by 5, that's 9.5, and so on. So You have the lower class boundaries, and we also have the upper class boundaries. So 9.5 is the upper class boundary of the first class interval. 14.5 is the upper class boundary of the second class interval, and so on. Now, the frequency. When we say frequency, this refers to the number of observations or the number of occurrences in a given interval. For example, in the class interval 5 to 9, that means there are 4 values that belong to the class interval. It might be 3, 5, and 1, 6, or any combination. Again, when we say frequency, this is the number of occurrence of values in a certain class interval. Next part is the class mark. When we say class mark, this is also called as the middle value or the value in between a class interval. So for this example, from the interval 5 to 9, our class mark is 7. And how do you calculate the class mark? You just have to add the lower limit plus and the upper limit divided by 2. So that's 5 plus 9 divided by 2. That is 5 plus 9 is 14 divided by 2. That's 7. You can also use the boundaries. No, the result will be just the same. So now, if your answer is in decimal or has decimal values, then you would just have to round it up, round it off to the same number of places with the interval. So since we have whole number here, so our rounding off should be to the nearest ones. Last are the relative frequency. Relative frequency can be expressed in its real value, which is in decimal places, or in percentage. How do we calculate the relative frequency? We will present it later on. Before that, we have to define it first. Relative frequency is the ratio of the frequency of the class interval, your class interval, divided by the total or the sample size. So our sample size, if we will add all of the frequencies, the sample size would be equal to 55. So to calculate the relative frequency, again, it is said that the the frequency of that class interval divided by the sample size. For the first class interval, our frequency is equal to 4, and our sample size is equal to 55. So we have to divide 4 by 55. Then you will get a result of 0.0727 and so on. Now, I would suggest to round it to the nearest 10,000s. Okay, so that would be 4 decimal places. Now, why? Because I would also suggest that you present your percentage in 2 decimal places. So that means you will be presenting it in the hundreds form. No, in when you are now converting the rational value or with decimal places to the percentage. Again, the second class or the second relative frequency can be calculated by dividing 7 by the sample size. That's 7 divided by 55, and you will get 0.1273 or 12.73%. If you will continue your calculation, you will have these data. Now, how do you check if you get the right answers or your calculations are correct? You sum all of the relative frequencies, and the sum or the total should be equal to 1 or 100%. Okay, here's an example on how do we create a frequency distribution table. As you can see in the previous slides, the data are already grouped. So the calculations are already done. Now, what if we will have a ungroup? We will have an ungrouped data, no, a raw data. For example, you have gathered data. So of course, those data which were not arranged are called ungrouped data. For this example, we will be uh, calculating or creating a frequency distribution table for the measurements that were recorded for the drying time, which is expressed in hours, of a certain brand of latex paint. Now, these are the data. If you will count all of them, you have 30 uh, data, no? 30 numbers here, 30 values. You have 3.4, 4.4 until 2.9. So how do we create a frequency distribution table? So aside from the parts, now we have to compute the different calculated values or parts, just like the K, which is our class interval, our range, and our class width, and the other values. So how do we calculate the class interval? To calculate class interval, which is K, that is 1 plus 3.32 times log of n. Though there are some statistical books which calculated class interval based on, uh, say, the square root of the n, no, which is your sample size. But for this course, we will be using this formula. Now, though the other formulas are also correct, but for us, we will be using this formula. We have k is equal to 1 plus 3.32 times log of n. And we have to express it in whole number. Why? Because this refers to the number of class intervals. Then, after, find the range, which is r, and this is equal to x sub max minus x sub mean. Uppercase x sub max refers to the largest value. Uppercase x sub mean refers to the lowest value of your data. Then to determine the class width, that is the range divided by the class interval. Now your class width should have the same number of decimal places of the data, and I would suggest that you round it up, not round it off. Okay? Then after calculating these first three fundamental values, we can then create the frequency distribution table, including the lower limits, upper limits, lower class boundaries, upper class boundaries, the class marks, and the relative frequencies. Okay, now this is now the finished table. So how did we calculate this one? If you will go back, you have there uh, our k is equal to 1 plus 3.32 log of n. What's the value for n? Based on our previous table, we will count these all. Our n will be equal to a our n will be equal to 30. Now I want you to get your pen and papers and calculators and calculate together with me. Okay, our n is equal to 30. Then how do we calculate for the range? Our range is again equal to the largest value minus the lowest value. We will check what's the largest value and the lowest value in our data. You have there 3.4, 4.4, 3.5. You have 2.5, 4.0, 3.4, 5.2, 2.9, 3.0. Then 5.3, 2.8, 2.7, and you have 5.6, 4, 2.5, 4.7, 2.8, 2.8, which means 5.6 is our largest value, 2.5 is our lowest value. So to get the range, that's 5.6 minus 2.5. And that is equal to, that's 1, and you get 3.1. So our range is equal to 3.1. Then how do we calculate for the class width? So the class width is equal to the range divided by the number of class interval. By the way, we have to calculate first our k. So our k is equal to 1 plus 3.32 times log of n. So if you are using your calculators, that will be 1 plus, put this in a parenthesis. So that's 1 plus parenthesis 3.32 times log of 30n. And you will get 5.904, or we'll round it off to 6, which means we will have to create 6 class intervals. Then let's go back to the class width. That's range over k. So if you will divide your range by your k, you will get approximately, or that's 0.517. Now, I would suggest that you round it up, again, round it up to 0.6. And that's it. You have now your class interval, you have your range, and you have your class width. So we can then create our frequency distribution table. So based on those values, going back, based on these values, k is equal to 6, r is equal to 3.1, class width is equal to zero point 0.6. So we can get the lower limits, upper limits, and so on. Now, what's your uh, again? We have 6 class intervals, and which number will we start? In each class, or in the first class interval, we will start with the lowest value. So our lowest value is 2.5. And based on that, our class width is equal to 0.6. So to get the next class interval, we will add 2.5 by 0.6. And 2.5 divided by plus 0.6 is equal to 3.1 plus 0.6, that's 3.7, 4.3, 4.9, and so on. When you get all your lower limits, that will be the time you can have your upper limits. So you just have to, if your lower limit of the next class interval is 3.1, you just subtract it by 1 based on the decimal place. Since we have one decimal place here, so we will subtract 3.1 by zero point 0.1. So that's 3.1 minus zero point 0.1, you will get 3.0. So this is your upper limit. Then you just add up your upper limit by the class width, which is zero point 0.6, and that's 3.6 plus zero point 0.6 is 4.2, and so on. Then you will now have your class intervals. If we will count all the class intervals, you have 1, 2, 3, 4, 5, and 6. Now check your lowest value, and the largest value should be uh, can can be found within the class interval. Our lowest value is 2.5. Our largest value is 5.6, which is found in the last class interval. Now, to get the boundaries are, again, take note that the boundaries should have one more decimal place compared to the class interval or the intervals. Since we have one decimal place in the class interval, that means our boundary should have one more place, decimal place. Okay? So how do we get the boundary? We'll start with the upper class boundary. So that's the upper limit plus the lower limit of the next class interval. Divide it by 2, you will get 3.05. Then the next upper limit, we'll just have to add it by 0.6, that's 3.65, and so on. Then you can get the lower limit of the next class interval. Now, the lower limit of the next class interval and the upper limit of the current class interval are equal. Now, take note of that. Boundaries rather, sorry. The upper limit of the class boundaries and the lower limit of the next class boundary, sh- lower lower class boundaries should be equal. Unlike the class intervals, the limits of the class intervals should not be equal, should not be the same. Now later on we will have in our next method we will understand the use of these boundaries. Again, your upper class boundary should be equal to the lower class boundaries of the next class interval. Then you will just have to subtract this one by zero point 0.6 and you will get the lower class boundaries of this interval. And add the next these next rows by 6 respectively. Then you will have these values. Now, the class marks. Again, the class marks are called the middle values. So we can get the class marks by adding the intervals, the lower limit and the upper limit, add them. You will get 5.5 and divide it by 2. You might get 2.75. But since we only have one decimal place, so that's 2.75. So we will round it off. That's why we got 2.8. Okay. Same with the next interval, 3.1 plus 3.6. That's 6.7. Divided by 2, you will get 3.35. So since our data has only one decimal place, so we will round it off. So we'll get 3.4. Okay, now how do we get the frequencies? So to get the frequencies, we have to count based on our data. For example, 3.4. So where can we find 3.4 in our class interval? So 3.4 is at the second class interval. So we'll put 1. We'll use tally type. Then you have 4.4. So 4.4 is at the fourth class interval. The next, you have 3.5. That's in the second class interval. Yeah, that's on the second class interval. Now you just continue counting them or tallying them, and you will get these data. You have from 2.5 to 3.0, there are 9 data. From for the interval 3.1 to 3.6, you have 6. Then 3, 5, 6, and 1. Count the sum of the frequencies again should be equal to the number of data. So since we have, if we will add these frequencies, we will get 30. Then the next step is to calculate the relative frequency. So the relative frequency is equal to the frequency of that interval divided by the sample size. So for this case, for the first class interval, our frequency or your small letter f, again, then this is your uh, small x, that's for this x sub I. So this is your small x sub 1, then your boundaries intervals, then this is your RF, so relative frequency. To get the relative frequency, again, that's 9 divided by 30, and you will get 0.3, or if you want percentage form, that's multiply this one by 100%, and that's 30%. 6 for the second row, you have 6 divided by 30, and that's equal to 0.2 or 20%. Now, take note that I use or here because 0.3 is not equal to 30%. We have only converted 0.3 to percentage by multiplying 0.3 by 100%. So we use or. So that's again 0.2 or 20%, 0.3 or 30%. Then we have 3 divided by 30, and that's 0.1. Multiply 0.1 by 100%, you'll get 10%, and so on. So it will be your task to calculate all of these. Remember, you have to put on the table number and the table name. So I put here table number 2, drying time of a certain brand of latex paint, which is expressed in hours. And these are my headers, my row classifiers, and the body. So I don't have any source because I might have taken it based on experiment. So that was uh, the frequency distribution table. Okay. Now another form of table, or the second method, is using the cumulative frequency table. So we have these parts. Now I will still be showing you the RF, though it's not necessarily to be here, but I would just have to show you how so that we can compare these values. So suppose we have this data. So this is based on our previous example. That's table. I think that's table 1. Now we have here the class intervals, our class marks, and we now have the frequencies. So to get the relative frequency, again, you have to divide the frequency by the sample size. And that's 4 divided by 60. So you answer that one. So you for this, as of this, we'll have to mm, use decimal place. It's all right. But remember, you have to use 4 decimal places. Next is the less than cumulative frequency. You have here 2 less than cumulative frequency and the less than cumulative relative frequency. So the difference is that the this one is based on the frequency. Your uh, less than cumulative frequency is based on the frequency. Your less than cumulative relative frequency is based on the less than cumulative frequency divided by the sample size. So to get the less than cumulative frequency, we will start with the first frequency. No, and that's 4. Then we will have to divide 4 by our sample size. That is, no, wait. Okay, we're talking with the less than cumulative frequency. Our less than cumulative frequency is equal to 4. The next less than cumulative frequency will be this frequency here plus the frequency of the next class interval. That is why it's called cumulative frequency, because the next value is based on the previous added by the frequency of the current class interval. So for here, you have 4 plus 7, and that is equal to 11. So our next less than cumulative frequency is equal to 11. Then the less than cumulative frequency of the third row will be this one, 11, plus the frequency of the third row, which is 11, and that is equal to 22. For the fourth class interval, that's 22 plus 15. So that's equal to 37. So that's cumulative. Now, when we say cumulative, you have to add the previous sum with the new value. Continue this one, and you will have a data. Your last answer should be equal to 60, which is your sample size. Now, how do we get the less than cumulative relative frequency? Just like the relative frequency, we have to divide the frequency of the row by the sample size. So to get the less than cumulative relative frequency, you have 4 divided by 60. So you will get that value, calculate it. Then the next is 11 divided by 60. Since this is our less than cumulative frequency, 11 is our less than cumulative frequency. So again, express it in 4 decimal places. Then the next um, cumulative, less than cumulative frequency is 22. Divide it by 60, and so on. Now, the last cumulative frequency will be 60 divided by 60, and that should be equal to 1. If it's not equal to 1, then you might have problems in, it might be your solution here, the previous uh, rows, or maybe in the frequency. Again, you have to check that the total value of this frequency, when you add them up, that's equal to your sample size. So that's for the less than cumulative frequency and less than a cumulative relative frequency. For greater than cumulative frequency, we will start with the largest value or the sample size. In the less than cumulative frequency, we started with the lowest frequency or the first frequency. So for greater than, we will start with the sample size, and that's 60. Sorry for that. Then you have the next will be this frequency subtracted by the previous frequency. So that's 60 minus 4. So you will get 56. Then for the third class interval, that's 56 minus 7. That's 49. So you continue subtracting until you will get the last value, which is 5. Okay. To get the relative frequency, the greater than cumulative frequency, so you will have to divide 60, which is your greater than cumulative frequency, by your sample size, which is also 60. So that's equal to 1. The next, divide 56 by the sample size. So get a value. Until you reach the last one, you have 5 divided by 60. Now you will have another value. So the result would be like this. By the way, this is how what I have discussed earlier based on this. So this is now our table for the cumulative relative frequency. Now, how do we interpret this one? For the greater than cumulative relative frequency, we can say that from the class interval, for the first two class interval, that's from 5 to 9 and 10 to 14, there are 11 of them, which is 0.1834 or 18.34% of our sample size. So if we would say from 5 to from the first class interval until the first class interval, that's 5 to 29, there are 47 of them. No, that's 78.3% of our sample size, and so on. Now, for the greater than cumulative relative frequency, it's different. No, it's in descending form. Okay, the last method is through stem and leaf method. So we will have to divide the number, your data, Now, one would be the stem, and the other uh, would be our leaves, no, our leaf. So this is now an example. This is an example of a stem left table. You have here zero. How do we read this one? You have the data are actually 3, 8, and 9. So the stems are our most significant number. The leaf is our least significant numbers. So for the second row, which means our data are actually 10, 11, 12, 14, 15, 16, 17, 18, and 18. So there are two 18s here. So in the stem and leaf method, you have to write all of the values. So as you can see in the third class, in the third stem, you have 20, 21, 23, 23, 25, 26, 27, 28, 28, and 29. Then in the last stem, you have 50 and 50. So that's how we interpret this table. So this is how we construct the stem and leaf table. First is to divide each measurement into two parts. So the most significant value or digit is the stem, and the least significant digits are the leaf. Then list the stems in a column in a vertical form. And for each measurement, record the leaf portion of the same row as its corresponding stem, or on its corresponding stem, order the leaves from lowest to highest in each stem. So you have to arrange them from lowest to highest. Then provide a key to your stem and leaf coding so that the reader can recreate the actual measurements if necessary. So if I would say, when we say key, for example, if I would say that my key is that the leaves are decimal values. No, if our leaves are in uh, this form, meaning one decimal place. So I would interpret this as 0.3, 0.8, and 0.9. Then the next stem or the next rows will be 1.0, 1.1, and 1.2, so on. So again, you have to provide a key. So if by default, if there are no keys found, then these are read in or interpreted in whole numbers. So that's it. We have the three different methods and under the tabular methods. You have again the frequency distribution table or method, the cumulative frequency distribution, and the stem and leaf. So that would be all for today. Okay. And see you on our next discussion.